Hey there, everybody. This is Mr. Piercy, and welcome to my lesson on Lagrange error bound. And this is going to be a video that's going to demonstrate how Taylor polynomials are going to be used to estimate the values of the functions, what Taylor's inequality is going to be to measure the accuracy of an approximation, and how we can use alternating series to bound the error of a Taylor approximation of the function. And if you are so inclined, here are some subsequent skills and uh, prior information things that we may need to have for the lesson involved. And let's just go ahead and jump into it here. So what we're talking about here is something called the Lagrange error bound and accuracy. The error bound is something that we've already talked about a little bit in a previous video for this course. But at this point in our study, we've talked all kinds of ways to approximate values of a function. And they're giving you some examples that is by no means exhaustive. You could look at a graph to get its estimation. You can do tangent line approximations, Euler's method, and the most recent approximation method has been Taylor and Maclaurin polynomials. So like I said, it's by no means exhaustive, but there's lots of ways that we can identify an approximation of something, excuse me, that may be easier to do than figuring out what the actual thing would be. Now, the Lagrange error bound, essentially what we've done, and you know, we'll talk about it a little bit more in the lesson as it comes up, but essentially what we're doing is, you know, there's an approximation and there's an error, and we take the approximation and we can add and subtract the error, and that margin is what's known, or that plus and minus difference, that's what's known as the Lagrange error bound. And the Taylor inequality, which we'll see here in a minute, is going to be something that we can use to help us figure out how accurate we're actually going to be to the proper, or to the actual function, whatever it happens to be. So here, when we use Taylor polynomial approximations, it's a good idea to know how accurate they are to the exact values. And the concept of the remainder is given to you here. So here, where they're talking about f of x, that is the exact value that they're referring to. When they say p sub n of x, that is what they're looking at as the approximate value that we got from our Taylor polynomial. And then we have the r sub n of x, that's the remainder. Now keep in mind, just again, just make sure that everybody is, maybe not do black here, the n that we're looking at here, that is the degree of your Taylor polynomial, okay? And sometimes it may be p sub n comma c of x, where the degree, of course, is n, and c would be where the Taylor polynomial is centered at, okay? Here, the error is going to be the absolute value of whatever the difference between the actual polynomial or actual function was minus its Taylor polynomial approximation. And that makes sense. When we use a Taylor polynomial, and for some reason here they're switching to t instead of p, which is fine. The variable really doesn't matter, but consistency might be an issue. If that throws you off, you can change that to a p sub n of x. Centered at x equals c to approximate a function f of x at some value a near the center. Okay. What we were able to conclude here is that if a function, or if the function equals a polynomial minus or plus the remainder, the actual function, this is just what we were seeing a second ago, where we were saying f of, and I should say f of a here, not f of x. And here they're using t, so I'll use t here also. T sub n of x a, because we're doing it in terms of a. Sorry, I'm just so used to writing x, plus r, the remainder uh, of degree, whatever, degree n at a, or of a. If the function is going to be whatever the polynomial approximation plus the remainder, then the remainder is going to be found by taking the function minus the polynomial approximation, which, that's essentially what we were just seeing on the previous screen there, of a is equal to f of a minus t of a. And we can also look at this as maybe being, the error is equal to the actual minus the approximate. So what I'm going to be looking at here, they're providing a graph here so we can kind of have a visual representation of what this would look like. So let's just say this waveform or this function, whatever it is, let's just say that is your function f of x. Okay. We can have an approximation like so, where at this point here, where they're the same, where they intersected each other, that is going to be when x is equal to c. That's the center of the polynomial. But the Taylor polynomial is not necessarily going to be used to give us we're not necessarily going to be using it to find what the value is at the center. Maybe we want something just to the right of it or just to the left of it. So x is equal to c. Well, c could be any number. It could be 9. Okay. Now, depending on the scale, maybe right here, this is where x is equal to a. Well, maybe at this point, maybe that's 9.3. Okay, we're using that to kind of determine between and this would be, let me do my green here. This would be the Taylor polynomial centered at c, whatever c, 9, I guess in this case. That difference between the actual and the approximate, that is what we're really going to be kind of looking at here. This is the error that we're talking about. So, and the closer I get to the center, the more accurate the error, or the more accurate the estimate approximation is going to be. The further away from the center, the least, or the accuracy starts to decline. So here, in order to use Taylor polynomials effectively, we'll use Taylor's theorem to estimate the size of the error, and the remainder given in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. This gives us a bound for the error, but not the actual value of the error, meaning that we know, with it, within, plus or minus some number. That's what the Lagrange error bound is going to be, and we'll see an example here. This is what Taylor's theorem is. Essentially, what we're given in the top, or I guess in the middle of the screen right now, but the top expression, that is just the general form of the Taylor's polynomial, where from and I don't want to do the same color here. So from here to here, all of that, this is the approximation part. Okay, and this bit right here, this is your leftover stuff. This is where your remainder comes from, or your error. Okay, it's just like any other number. And no matter how far it is, if you say 3.3333, at some point you have to round it off. So this is what the approximate is. It could be a very, very close approximation to the to what the answer is, but at some point we have to cut it off, and all of those repeating 3 decimals, that's what's left over. That's where the error is going to be for our values. So what Taylor's theorem is saying is that if a function f is differentiable through an order of n plus 1 in an interval containing c, meaning that, remember here, n is the degree, okay? Meaning that one more degree, because you're seeing here, this is the function. This is like to your first degree, second degree, nth degree. So if we're saying n plus 1, n plus 1 is where you're going to kind of wind up here to say the n plus 1 degree. Then for each x in the interval, there exists a number a between x and c such that we're going to kind of wind up with this approximation value here. And when we write that kind of in a little bit more simplified manner here, we wind up with this whole thing here, where this is what we're using to identify as the remainder. Now what we're looking at here, this bit right here is going to be what we refer to as the maximum. That's the maximum value that we're going to wind up getting when we have, this is the n plus 1 in parentheses is showing you that that's where we're going to have, the degree of our polynomial plus one more degree. And that is going to represent the maximum, which, we just use a capital letter M in this case to represent the maximum. But that's the expression that we get according to Taylor's theorem. But, excuse me, one of the things that we're really going to be taking a look at is, pardon me, I got something in my throat, where we're really going to be talking about finding the accuracy of the approximation. That's where we're going to get into what's known as Taylor's inequality. Now, instead of finding the exact error of our approximations, we'll use two rules that help us find the upper bound for the error. In this way, we will know that the most our approximation is off the actual mark. So the first thing that we're looking at here for our the two rules that we have is that first is if you happen to have an alternating series. If the series is an alternating series, the error will be no greater than the absolute value of the first unused term. Okay, here the error will be no greater than the absolute value of the first unused term. And that's kind of what we were seeing in a previous lesson. I can't remember the number off the top of my head. It was from our Unit 9 material. I want to say it was towards the end, maybe section 4 or 5. Anyway, if it happens to be, this is the second rule, if it is a non-alternating series, is approximated, we will use a Taylor's inequality theorem. So for non-alternating series, we will use Taylor's inequality theorem, which is where we're getting the Lagrange form of the remainder. And it says it's stated below, so those of you following along with your notes, it's going to be right underneath here. And there we go. There's the Taylor's inequality expression. And there we go. So here, this is where we're getting that M that I was referring to earlier, the maximum. And of course, C is going to be the center. So this would work the same for a Maclaurin process as opposed to using the Taylor method. The only difference is that the center would be C or 0 for a Maclaurin series, but M for maximum is defined to be the maximum value, the degree plus 1 function times a, where a is going to be some number between x and c. Uh, and of course, c of course is the error. A is going to be some number, you know, that's close to c, but not exactly c. And bounds on the remainder found using this form are called the Lagrange error bound. And that's where we kind of take the uh, whatever the error is and we add it to our approximation, and then we subtract it to our approximation to find what the range of the error is going to be. It could be within this number to this number. For n is equal to 0, Taylor's theorem states that if f is going to be differentiable in an interval containing c, then for each x in the interval there exists a value a between the two such that we wind up with f of x is equal to f of c plus f prime of a times x minus c, or we can look at f prime of a as the difference of f of x minus f of c over x minus c, which we've been doing that a lot in calculus. It's been a little while since we had to find the difference quotient, but same idea. Now let's move on here. Here's some vocabulary that we need to make sure that we understand. So in this case, M, capital M, represents the maximum absolute value of the n plus 1 order derivative on the interval between, well, wherever the a value is, somewhere between x and c, that's where the a value is going to be. And we can find the maximum by substituting, in this case, the a value between x and c such that it maximizes the expression. Here, the expression, and this is coming from whether you're looking at the Taylor's theorem or the Taylor's inequality, these are going to kind of both be represented in them. The expression, the absolute value of x minus c to the power of n plus 1, the degree plus 1, over n plus 1 factorial, in this case is going to represent the first unused term, the next degree term in the Taylor series. And the product of the expression times the maximum of the absolute value is, in this case, going to tell us, now where did I have this saved? There we go. It will tell us a safe upper bound for the next degree term's derivative at x is equal to a. If the maximum times the absolute value of all of that stuff, f of n plus 1 times a on the interval between the center c and the value x is equal to a is not given or easily found, then we want to choose something that is reasonable but will be greater than whatever the expression is for f, the n plus 1 degree times a. And if you don't know the maximum or the interval, assume the interval is going to be the center of your x value that you're using. So in some instances, you're going to be given a problem where the interval may not necessarily be given to you, so the center of it needs to be on some interval, and you can just kind of make an interval that's going to be reasonable to work with. Two facts about the error. First, if we increase the number of degrees by adding more terms to the polynomial, the remainder will get smaller. The further that you go out in your degrees, the more accurate your approximation is going to be, so the remainder becomes a smaller value. Second, as we move away from the center, however, as we move away from the center, the error itself is going to increase. Now here, like I told you, at least I think I told you, we want to have a calculator for some of this stuff because you're going to just wind up with some very funny looking decimal numbers that you're going to want to be able to save them so that way your rounded approximation is going to be as accurate as it could be. In this case, the function f has continuous derivatives for all real numbers x, and it's telling us to assume f of 3 is equal to 5, f prime of 3 equals 2, second derivative is 3 is equal to 4, and the third derivative of f of 3 is equal to 7. So it's asking us to write a third degree Taylor polynomial for f about the center x equals 3, and use it to approximate f of 3.2 and to round your answer to 3 decimal places. Okay, so let's see. I know I had some stuff typed here. I just don't remember where I had it typed. Or maybe I'm just completely fooling myself. Maybe I just thought I typed some stuff up. So let me pause the video real quick and add some information so you don't have to watch me write it down. Okay, so this is, I guess I thought I had this part typed up, but I didn't. This is what we would use for a third degree Taylor polynomial. We would take the general form of the Taylor polynomial and write it out to the third derivative using the information that they gave us. So in this case, x is equal to c, or x is equal to 3, so that's really my center. What it's telling me is that here, the center is at 3. So when I'm looking at if that's the center, then I'm going to have some expression that says x minus 3 to represent the center. And that's kind of what I'm going to be using for my substitution here. So in this case, we're going to say f of c, in this case, would be f of 3, so that's just their 5. And here we're going to say f prime of 3, in this case, is going to be 2 times x minus 3. And keep going. We have f double prime of 3, in this case, is going to be a negative 4 over 2 factorial times x minus 3 squared plus, and f triple prime of 3 in this case is going to be plus a 7 over 3 factorial times x minus 3 cubed. Now in this case, x is equal to 3. And it's asking us to evaluate it for 3.2. So the center is at 3. So when I substitute, I'm going to take that 3.2, and that's what's going to wind up getting substituted in for all of these x's. So we're going to essentially just say 3.2 minus 3, which would just be a 0.2. So on my calculator, this is where I'm getting my approximation here. We're going to say the third degree Taylor polynomial approximation of 3.2, in this case, will be 5 plus 2 times 0.2. We take the difference of 3.2 minus 3, minus, and negative 4 over 2 factorial, that'll just be a minus 2, so minus 2 times 0.2 squared. 7 over 3 factorial doesn't really simplify. That would just be plus 7 over 6 times 0.2 cubed. 0.2 cubed. There we go. And we're going to just type all of that into our calculator, and we're going to get approximately 5.329. Now that number is, of course, rounded on paper. But the number itself that the calculator gives you, we want to save that number. We want to save that number on our calculator. Now, going on to the second part here, it says the fourth derivative satisfies the inequality of saying that f of n plus 1, that's where the 4 comes from, 3 plus 1, times a is going to be less than or equal to 35 for all x in the interval from 3 to 3.2. Use this information to find a bound for the error found in A. Okay, this is where we're going to start using the Taylor inequality that we were talking about. So in this case, the 35 is essentially going to be the maximum. So let's just, start it off. Let's not skip anything. We have r sub n of x, in this case, is going to be equal to the absolute value of f of n plus 1 degree of times a, and we're going to multiply that by x minus c to the n plus 1 power also, and all of that is divided by n plus 1 factorial. That's what Taylor's theorem is going to give us. Now, based off of what we're looking at here, we know that we were working with a third degree polynomial, so I'm going to start here by replacing the n with 3. And that's how we're going to get f of 4 here, because the 3 plus 1 is going to give me a 4, times a times the x minus c to the power of 4. And in the denominator, we're going to wind up again with 3 plus 1, so I wind up with 4 factorial in the denominator. Now that expression itself, based on what they're telling us that this whole thing has to be less than or equal to 35. So that is where I'm understanding that, that 35, that's essentially going to be the maximum. So I'm going to take this 35 and I'm going to come and I'm going to substitute it right here where I have the f of 4 times a, or f to the 4th degree times a. Okay, so I wind up with this, and I'm going to just kind of go to the right here, that expression is going to be less than 35, the absolute value of 35 times the x minus 3 to the 4th power over 4 factorial on the interval from 3 to 3.2. Okay, well, now that I have that expression, we're going to be able to use that expression to kind of give us a value that we can use for our remainder. In this case, now we're going to take our value that they're giving us for x, and we can substitute it into the expression. So the remainder in this case, what we're talking about, the remainder, the absolute value of the remainder of the third degree polynomial at when x is equal to 3.2 must be less than or equal to this expression that we just got, the 35 times x minus 3 to the 4th power over 4 factorial. And of course, now I'm going to replace the x with the 3.2 value that we have. So we have 35. So 3.2 minus 3 will be 0.2 to the 4th power over 4 factorial. And at this point here, I have to go to my calculator if I actually want the decimal value. So here, that decimal value is approximately going to be 0.0023, and it's repeating at that point. And again, I want to take that number, I want to take that decimal number, and we want to save it on the calculator. Because what we're going to use is we've gotten an approximation with our third degree Taylor polynomial. We've established a value for the remainder, a value for the error of 0.0023 repeating. And now we can take that to help us establish our bound for the Lagrange error bound. And that's what part C is asking us to do. And that's really why we wanted to save those numbers on our calculator. Find an interval from A to B such that A is going to be less than f of 3.2, which will be less than or equal to B, and give three decimal to round it to 3 decimal places. So in this case, the f of 3.2, that is the approximation that we got because we don't actually have a function f. We don't know what function f is going to be. So here, when I'm saying that f of 3.2, where we're going to say f of 3.2, this is really our approximation. Okay, that has to be less than or equal to the number that we just got added to f of 3.2. So I'm going to say f of 3.2 plus that remainder that we just got, the remainder at 3.2. But it also has to be greater than or equal to the approximation 3.2 plus, nope, not plus, minus the remainder at 3.2. And this is really why we wanted to save those numbers on your calculator because they're not going to be very nice numbers. Now it does say round it to 3 decimal places, and if you take the 5.329 number that you saved on your calculator and you add the 0.0023 repeating number that you saved on your calculator, you're going to get something that has a repeating number, if I remember correctly, but I just wrote it out on my paper as 5.332. And if we take the difference of those two numbers, I get exactly 5.327. Okay? So here, where we're finding the interval, that is the Lagrange error bound. Can f of 3.2 equal 5.331? Sure it can, because the error, the Lagrange error bound that we got was between 5.327, so you can think of like this is the A value that they said, and this is the B value that they gave you, going back to, the A and B here. So can you have an output of 5.331? Sure you can. It's on the error. It's on that interval. Can you have a value of 5.334? No, it's not on that interval. So there we go. And taking a look at our next example, it's asking us to, again, and we definitely want a calculator for this, estimate the sine of 1/2 using a Maclaurin polynomial, so it's centered at 0. Excuse me, what is the least degree of the polynomial that assures an error smaller than 0.001? Okay? Well, in this case, because it's telling us the margin of error that we want or that we need, the margin of error has to be less than this. That tells me that we're going to be using the Taylor inequality expression that we had. Now in this case, we're going to amend it a little bit for our Maclaurin polynomial because it doesn't matter to say x minus c in a Maclaurin series because the center is at 0. So in this case, I'm going to say the absolute value of r of some degree that I don't know because that's what it's asking me to find. What degree do I need? And this one actually has, it's you'll see the answer that we're going to wind up with here. This one's going to be interesting. So here, the remainder of some degree that we don't know of x has to be less than or equal to the absolute value of the maximum. That was at f of n plus 1 times a. The maximum multiplied by, now here this is where the Taylor inequality has in parentheses x minus c, but in this case it's just going to wind up being x to the n plus 1 power instead of x minus anything. And that will be over the n plus 1 factorial. Now that expression, based on what they're telling us, must be less than, not whether we say less than or equal to, it doesn't make a difference. You know, it's saying smaller than 0.001. Okay, so let's see what we have. In this case, we're looking at it when we're estimating it at 0.5. So here, I'm going to say r of some degree that I don't know of 0.5 has to be less than or equal to the maximum value. Now, what is the maximum value in this case? They're not really telling us what the maximum value is. Now, in this case, the maximum value of a sine function is based on what it's, you know, the domain is everything, but the maximum that it could go to on the y-axis typically is going to be 1. That's where it's bound to top and bottom, positive 1 or negative 1. So I'm going to be looking at m to be equal to 1 based on the fact that this is a sinusoidal function. The output is going to be no greater than 1, less than or equal to 1. So in this case, m is equal to 1, and we're going to say times x. So x in this case is the 0.5, and we're going to do it to the n plus 1 power. We don't know what n is. We don't know the degree. So this will be in the denominator, n plus 1 factorial as well, but it still has to be less than 0.001. Now here, this is where I would say, okay, well, if you had an algebraic approach to try and solve for n, go for it. But this one doesn't really make sense to try and apply this one to an algebraic approach, especially since they're telling us we should be using a calculator. Excuse me. So this is where I'm going to use my calculator to figure out what value of n will, if I substitute it into the expression that I have for the remainder, what value of n will give me something that is less than 0.001. So this is where we're going to go to our calculator. We're going to say n, and we're going to, so my output was the 0.5 to the n plus 1 power over n plus 1 factorial. So I'm going to just go to my calculator and say, okay, when n is 1, what do I get when I substitute it into that? And I got a 0.125. When n was 2 for my degree, I got a 0.02083 repeating. So we're still not less than 0.001. For the third degree, I got a 0.0023. So the decimal place is moving, but it's still not less than 0.001. So let's see, 4 in this case gives me 0.00026. So at that point, when I have a fourth degree polynomial, I will be less than 0.001. So the remainder, the error, is going to be accurate to 3 decimal places. So this is what we're looking at for the answer. The question that we were asked is, what degree polynomial do you need in order to have a remainder that will be less than 0.001? Well, in this case, n, the degree, has to be at least a fourth degree polynomial. So n is equal to 4 is the smallest degree Maclaurin polynomial for the error to be less than 0.001. Now, this is where I was kind of alluding earlier to. Well, this one's going to have a very interesting answer. Mathematically, the fourth degree polynomial is going to be the smallest degree Maclaurin polynomial for the error to be less than 0.001. But um, let's recall what was the actual series for a Maclaurin polynomial. Do you remember what the Maclaurin series is for sine? Well, if we were to, take the Maclaurin series and write out its Taylor polynomial for this one, for sine of x, we wind up getting a Maclaurin polynomial of m sub n of x. This is what our Maclaurin polynomial, this is one of the three Maclaurin polynomials you're expected to know, or the Maclaurin series that you're expected to remember. It was equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. This is an alternating series, but it only uses odd degreed polynomials. It only uses odd degreed expressions. So clearly the fourth degree is going to be the smallest one, but if it's a Maclaurin polynomial, I think it really should probably say that it is the fifth degree, because specifically for sine of x, the even degreed terms are excluded. So if the fourth degree was excluded and we tried stopping at that point, I would argue that we are stopping at the third degree polynomial, which would not satisfy the equation or not satisfy the problem. So this is a very interesting conclusion, and I'm not entirely sure on which way I should go with the answer, other than maybe including both of them. And say that, well, according to what we know for the remainder, we would have to have a minimum of 4 degrees for this particular problem to have a degree or an error less than 0.001. But because it is a sine function and we're talking about a Maclaurin function, a Maclaurin series for sine of x, and even numbered terms are not used, then I would probably say that fifth degree is where we would need to go. And it's similar in my thinking to, like cars, like how many cars were sold, uh, in such and such period of time in such and such country or whatever. They're always going to be whole numbers. You don't have like a third of a car that you sell. You either sell a car or you don't sell a car. Um, ask a car salesman, if you know one, when was the last time you sold 7/8 of a car to somebody? You either sell them a car or you don't. So I'm going to probably err on the side of caution and say that, yeah, fourth degree is the minimum that we would need, but because this is a Maclaurin series for sine of x, the even degree terms are missing in the alternating series, so we would probably have to go up to a fifth degree on that one. So, like I said, a very interesting problem. Hopefully, I'll be able to think about it a little bit more and maybe make an update to this later at some point and go from there. Take a look at the third example here. Let p sub 3 of x, so the fact that they're saying p sub 3, they're telling us that it is a third degree polynomial, and there it is in words as a third degree polynomial. Maclaurin polynomial specifically, so it's centered at 0, using the information from the graph, and that the graph is going to be the absolute value of the fourth degree polynomial, showing that p sub 3, the approximate, minus the actual at 1/4 is going to be less than 1/400th. Okay? So here, this is an interesting problem because if you notice, they're not really giving us an interval. The interval could probably be approximated from the graph, but they're not really giving us an interval. And they're also not really giving us any kind of a maximum value to use. So this is how I'm going to think about starting this problem based off of the information that they're giving me. Since no interval or maximum is given, so what I'm going to do is I'm going to use the fourth degree polynomial function with center at 0. And in this case, I'm going to use a maximum of 15, where we have that local maximum. I'm just kind of approximating it on that quadratic portion there as a reasonable value to be greater than f of 1/4. Okay. So how are we going to take a look at this? Well, again, we're going to be using the Taylor inequality, or modified for a Maclaurin polynomial here. So I'm going to wind up with, let me turn my pen back on, the absolute value of r sub n of x must be, in this case, less than the absolute value of the maximum, capital M, times x to the n plus 1 power over n plus 1 factorial. And whatever that error is, that error has to be less than 1 over 400. 400. So let's take what we know. In this case, we're going to say we're working with a third degree polynomial at when x is 1/4. And the maximum that we're taking from the graph is about 15, around that area. And because this is a third degree polynomial, we're going to say 3 plus 1 for our exponent value. So this will become x to the 4th power over 4 factorial. And that has to be less than 1 over 400. And again, this is really where I'm going to kind of jump onto the calculator here to see what we get. There are some math things that we could do with this. For instance, in this case, when I substitute the 1/4 for x, so let's go ahead and substitute the 1/4 for x, 15 times 1/4 to the 4th power over 4 factorial to be less than 1/400th. Well, 4 to the 4th power is 256. So I can rewrite that as saying 15 over 4 factorial times 256. And we could try simplifying it, but again, really just, let your calculator help you out with this one. And when we simplify the absolute value, I'm getting 0.0024 to be less than, and 1 over 400 as a decimal is 0.0025. So the value of the remainder that, or the value of the maximum that we got, approximating, guesstimating it to be about 15, will indeed satisfy the condition that was given to us by the problem, where the remainder is going to be, the error that we have is going to be less than 1/400th. And that is how we're going to finish off looking at this problem. Now this is a really good problem. This is a nice, challenging problem. And those of you following along with your notes, maybe they're not going to give you enough space on your paper to work this one out at least the way that I thought my way through it. If an error calculation is required on the AP exam, all work must be shown, so the calculator can only be used as a method to check your computations. So even if you can figure out what this is going to be on your calculator, if you can't show your work for it on a free response question, you're still not going to get credit for it. You might get a point if you have it right, but without the work, you're not getting full credit. Use the Maclaurin series for y is equal to x to estimate 1 over the square root of e accurate to 4 decimal places. So let's take a look at this one here. And this is going to be a very interesting problem. Like I said, it's something that you may not have enough space for on the paper, provided for you on the handout for your notes here. All right, so estimate 1 over the square root of e to 4 decimals of the Maclaurin series y is equal to e to the x. So in this case, what we're going to look at, because it's a Maclaurin series, we want to know, in this case, what remainder are we going to be looking at? So that way we can, kind of going back to what we were just doing here, where we were looking at the remainder within to 1/400th. We're basically going to be have to do something like this again, except instead of saying that the remainder has to be less than 1/400th, in this case it has to be something less than 4 decimal places, so like maybe 0.0001 or something like that. Okay, so we understand that for a Maclaurin series, the remainder has to be less than or equal to the absolute value of the maximum times x to the n plus 1 power over n plus 1 factorial. So we have to understand that for our, in this case, because it's just Maclaurin, we're looking for the error. We have to have something that's going to be less than 4 decimal places. So in this case, we're using a known value, a known quantity, y is equal to x, to help us estimate that. Well, what we would do with the y is equal to x expression, if I were going to use y is equal to e to the x as my expression here, I'm going to say f of x could be equal to e to the power of x. And essentially what we would do to create the Maclaurin polynomial for this is we would just kind of keep taking the derivative. So I would say, the first derivative of e to the x would just be e to the x. The second derivative of e to the x would be e to the x. The third derivative of e to the x would be e to the x, and so on. So here, in this case, f of any derivative of the expression e to the x is just going to be e to the x. Okay? Now, what this is letting us know here is that here, this is where we're going to be able to identify what the center of our expression is going to be. In this case, the center of our expression is going to be when x is equal to 0. So if the center is when x is equal to 0, which is kind of implied since it's a Maclaurin polynomial, then I can recognize that if I'm looking for a maximum, I can say the maximum here is going to be the absolute value of e to the x when x is equal to 0. Well, when x is equal to 0, that just tells you that the maximum in this case is going to be a 1. Anything to the 0 power is going to be a 1. So it's centered. The maximum in this case is going to be a 1. And, well, what interval is it going to be on? Well, the fact that it's centered at 0, and here, in this case, well, let's look at what the function is. We're looking at this here. Y is equal to e to the negative 1/2 power, essentially. In this case, I want my, since that's the x value that we're kind of, evaluating with, we're looking at something at x as that exponent value. I'm going to look at my interval, where it's going to contain the center, but it definitely needs to contain the x value that we're looking at here. So I'm going to look at my interval here for -1 to be less than or equal to x, because that will contain the negative 1/2 that was given to us by this guy here. And so now I have an interval, if I need it, with which to work. I have my center of 0, and because we're evaluating it at 0, x of 0 is, or e to the 0 power says in this case I'm going to have a maximum value of 1. So now I have some information that I can take and substitute back into my remainder expression. So here, coming back to this, I'm going to say the absolute value of r sub n of, what was it, x is equal to the maximum value, which in this case is a 1, times x to the n plus 1 power. And in this case, we don't know what the degree is. They're not telling us anything about a degree. We have to kind of figure that out a little bit here, kind of like what we did going back to the problem here with the sine. They didn't tell us what the degree was, but we know an approach that we could take a look at to identify what the degree is going to be. So we're just using that strategy here now. So I'm going to just say x to the n plus 1 power over n plus 1 factorial, but this is going to have to be less than or equal to, less than, in this case, 4 decimals. So I'm going to just say 0.0001. There's 4 decimals. Okay, so, well, it does say less than, so let's get rid of the equal to part. There we go. Now, this is where we're going to kind of go back to our calculator and using that strategy like we did with our sine function, where we wanted it, figure out what the degree was going to be. We're going to do the same thing here. I'm going to just kind of make a table where in this case, we're going to say, in this case, x is going to be the 1/2. So 1 times 1/2, we're going to say 1/2, and is, you know what, let me clean this up just a little bit. Let me back up a tad here because I'm in my head I know where I'm going and I'm not writing something down and I want to make sure I get everything written down that needs to be. The value of x in this case is that negative 1/2. Okay, so here I'm going to have 1 times negative 1/2, so that doesn't really matter. The 1 doesn't matter, I mean. N plus 1 over n plus 1 factorial. It has to be less than 0.0001. Now, in this case, here, specifically, I'm looking at the negative sign, and I kind of went too far on the negative. Kind of covered up the negative sign. Because it's dealing with an absolute value, we're going to just lose the negative because it's inside of an absolute value. So it really doesn't make a difference. Okay, so my final expression here in this case, going back to my purple color, is going to be, and I keep writing an equal sign here, and that should be less than or equal to, the remainder should be less than or equal to. So we'll just say 1/2 positive because it's inside an absolute value, so everything's going to be positive anyway, to the n plus 1 power over n plus 1 factorial. N plus 1, let me just erase that because that's not working. N plus 1 factorial. There we go. And it has to be less than 0.0001. Okay. So now I have my expression that I'm going to kind of use to help me figure out what degreed polynomial do I need in order to have the error accurate to, less than 4 decimal places, something that's going to be less than 0.0001 in this case. So this is where I'm going to start making my table using my calculator where n is going to be some value. The expression for my output is just going to be that 1/2 to the n plus 1 power over n plus 1 factorial. And again, we're just picking some numbers. When n is equal to 1 on my calculator, actually, no, I didn't start at 1 because I realized when I did it at 1, it was way, way off. So it wasn't even close. The first one that I really am going to be looking at is let's try n is equal to 3. At n is equal to 3, I got 0.0026, which, didn't work. It's not less than 0.0001. So we just keep going. At 4, I got 0.00026, so closer, but not yet. But if I go to a fifth degree polynomial, I get 0.00026, which is definitely less than this guy right here. Okay, so in this case, the degree has to be 5, minimum. And if you recall what the Maclaurin series was for the known stuff, you will recall that very much like the sine example that we saw earlier, it will use odd degreed terms in our polynomial. So the even degreed stuff wound up getting left off. So we know we have to have at least a fifth degree polynomial. Okay, and let's see, I don't know if I have space to kind of write here on the side. Let's see if we can get it in here. All right. So this is what we're looking at here. We got to recall some information. Recall. My hand touched the board when I was writing it with my pen. Got a little funny here. Uh, for y is equal to e to the x power, uh, as a Maclaurin series, is this. We have our summation from n equals 0 to infinity of x to the power of n over n factorial. And in this case, if we're going to substitute our expression, where in this case we wind up with e is equal to e to the negative 1/2 power. This is what we're going to wind up substituting for x into the expression for our series. So in this case, it's going to be using that known series to give us our approximation here of n is equal to 0 to infinity. In this case of negative 1/2 to the power of n over n factorial, which can be separated out a little bit to show n equals 0 to infinity, negative 1 to the power of n times 1/2 to the power of n over n factorial. Now the general expression that we have for y is equal to e to the x is simply going to be, it'll be 1 plus, in this case, x over 1 factorial. You don't need to write the 1 factorial, I guess. And here, the next one in the series would wind up being plus x squared over 2 factorial plus, I'm sorry, I said this is alternating. It's not alternating. I don't know why I said it was alternating. X cubed over 3 factorial. And we're going to go out to the fifth degree here. And this will be x to the 4th over 4 factorial plus x to the 5th over 5 factorial. So now we've got it out to the 5th degree expression. So here I'm going to be able to substitute. I'm going to take that negative 1/2, and again I'm going to substitute it anywhere I have for x. So the 5th degreed polynomial in this case will give me 1 plus a negative 1/2 over 1 factorial, which is just 1, plus negative 1/2 squared over 2 factorial plus negative 1/2 cubed over 3 factorial plus negative 1/2 to the fourth power over 4 factorial running out of space plus negative 1/2 to the fifth power over 5 factorial. And we will, again, kind of go to my calculator here. And I would say that this is going to be approximately equal to, where is my number written down? In this case, I am getting a 0.60651,047. And I can get that number from the polynomial or by using my calculator with the series that we wrote here. Either one is going to give you the number. The series is probably going to be a little less time consuming to type out on your calculator. And so what is that going to be compared to? Okay, well, we're comparing it to 1 over the square root of e. So on your calculator, if you type 1 over the square root of e, here I am getting 0.6065 3066. Well, what did we do? We're looking for a Maclaurin series that will estimate the value of 1 over the square root of e to 4 decimal places. Well, by starting off with our error, okay, by starting off with our error and saying that it had to be less than 0.0001 4 decimal places, we were able to establish that we needed at least a 5th degree polynomial that would be accurate to within 4 decimal places. And once we had that, we used our prior knowledge for the Maclaurin series of y is equal to e to the x power to help us create a series that we could use to, a series that we could use to get our approximation, or get a polynomial that we could use to get our approximation. But either way, we got an approximation that was accurate to 4 decimal places. So I think that's pretty cool. I think that's a pretty good way of, thinking your way through a problem. I like that one a lot. Okay. Now, our last example that we're going to be taking a look at here in the Lagrange error bound inaccuracy is going to, again, kind of tie some things together. It's going to ask us to work a problem start to finish, where we're going to be looking at creating in this case, a 4th degree polynomial, and where we'll go all the way through to determining what the Lagrange error bound is going to be. Now, feel free to try and pause the video at any point and see if you are able to write the 4th degree polynomial that we would be looking at here, and hit play whenever you're ready to go. But presuming that we have this, again, Maclaurin polynomial with cosine, one of the 3 that you are expected to remember. So here, recall that in this case, if I have f of x being equal to cosine of x, that gave us a series n equals 0 to infinity, alternating -1 to the power of n times x to the 2n power, because this one uses even degreed where sine uses odd degreed terms of your polynomial. And in the denominator we had 2n factorial. And if we expanded that out, we are getting 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus etc., etc., etc. And we're asked to write a 4th degree polynomial, which if I kind of take my line here, if I just kind of went here, I'd say I can really kind of stop here, right? And all of this stuff would be my fourth degree polynomial, and this might be something that I could use as my remainder for my error. Remainder, that looks like too much like remember. Remainder, maybe that's something that we can use here. But anyway, we're asked to write a fourth degree polynomial, so let's go ahead and do that. Let's go back to the green. So the fourth degree polynomial, in this case, for cosine of pi over 12, this is where we're going to just substitute pi over 12 anywhere I had x in my general polynomial here. And in this case, I'm going to wind up with 1 minus pi over 12 squared over 2 factorial plus pi over 12 to the fourth power over 4 factorial. And that is what we should have for our fourth degree polynomial. The only other thing, and use it to compute. Okay, so yes, it does ask us to do that. Use it to compute cosine of pi over 12. So that would be approximately equal to 0.965925826. So there we go. There's the approximation of cosine of pi over 12. And just like what we've seen with some previous problems, you want to make sure that you save that number on your calculator. So part B, now what it's asking us to move on to, it says use the Lagrange error bound to show that the actual minus the approximate is going to be less than or equal to 1/5000th for the interval from 0 to 1. So here they're giving us an interval that we're going to use. We know that the center is 0 because it's Maclaurin, and because in this case it's going to be cosine again. Just like sine, cosine has a maximum output of either a positive 1 or a negative 1. So since we'll just focus on the positive 1 for absolute value purposes. And so I know that the upper bound, the maximum that I'm going to have for cosine, in this case, maximum for cosine is just going to be a positive 1. Now in this case, we're going to be looking for, let's go to a different color here. We're going to be looking for, we need to know at this point here, the Lagrange error bound, we need to know what is the error. Error, remainder, whatever you want to call it, what is that going to be? So, and we've done this a couple of times already in this lesson. So again, feel free to pause the video and see if you can get the error before I do. And in this case, we're going to be looking at the general form for the Taylor inequality, as it would be for a Maclaurin series in this case, is going to be the absolute value of the maximum times x to the n plus 1 power over n plus 1 factorial. And in this case, it needs to be less than or equal to 1 over 5,000. Okay. So they told us in part A that the degree was 4. So we don't have to try to figure out the degree here. They told us that the degree was going to be 4. And the one thing that we don't really know is, actually we do, because it told us, yeah, we do have a value for x of pi over 12. So let's start plugging away and see what we get here. So the maximum value is 1 for cosine. In this case, x that we're evaluating it for is pi over 12. N in this case is going to be 4, so 4 plus 1 is going to give me to the 5th power here, so I have 5 factorial in the denominator here, and it has to be less than or equal to 1/5000th. Okay, well let's see what we end up with. So here, pi over 12 to the 5th power over 5 factorial. There's no way I'm going to attempt to do that on my own. We're going straight to a calculator. So pi over 12 to the 5th power divided by 5 factorial. When I did that on my calculator, I am getting 0. Let's see, I had 0, 0, 0, 0, 1, 0, 2, 4, 9. That's what I got from the absolute value expression. And I'm going to go ahead and divide 5,000, 1 divided by 5,000 on there, and I'm going to get 0.0002. So we are good. We are definitely getting the 5th degree. The first unused term is definitely going to be less than 1 over 5,000. So looking at this here, looking at that right there, 4 zeros in a row, says that in that case we should be accurate to 4 decimal places, okay, for whatever approximation that we would be looking at. And that's, so use of the Lagrange error bound to show that, okay, so we're good. We did what we needed to do here. The next thing it's going to ask us to do, it says use the 4th degree Taylor polynomial that we got in part A. For cosine of x about x is equal to 0. Again, they're just saying that the center is 0. To find an approximation for cosine of 0.8 and use Taylor's theorem to determine the accuracy of the approximation. Okay, so here what we had from part A, the polynomial that we got was, of course, cosine of x was equal to, this is my Maclaurin, and we did it to the 4th degree. We wound up with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. That was the polynomial that we got. So we're going to use that to approximate cosine of 0.8. So here I'm going to say cosine of 0.8. So that would be 1 minus 0.8 squared over 2 factorial plus 0.88 to the 4th over 4 factorial. And again, calculator time. Plug this stuff into your calculator, and I am getting 0.697066667. Okay. Now, that is the value that we're approximating for the function that we got of cosine of 0.8. Okay, that this is an approximation. All right, but now it says, and use Taylor's theorem to determine the accuracy of the approximation. Okay, so let's do that one in another color. So here, use Taylor's theorem to determine the accuracy in this case. So in this case, the accuracy is the next term. The absolute value of the error, which is what we're looking for. We're looking for the error. That's how we determine how accurate we are. In this case, has to be less than or equal to the absolute value of whatever the next term is. Next term. Okay. Now, this is where I was kind of telling you that, you know, this is an alternating series. So going back to part A, we probably wanted to use that bit there as what we would use for our remainder, for our error, to help us determine what the accuracy is. So we already know that it should be x to the 6th power over 6 factorial. So let's see, here we're going to say it has to be less than or equal to x to the 6th power, or the absolute value, over 6 factorial, because in this case we do have a minus sign in front of the term. And in this case, I'm going to say absolute value of 0.8 to the 6th power over 6 factorial. And if I type that into my calculator, here I'm saying that the area is going to be less than or equal to 0 .00036408.9. So both of these numbers here, this one here and this one here, we definitely want to save it in our calculator because in this case, the .697066667, that's the value that we're approximating with our Taylor polynomial, and we're going to use the next term, the .00003 blah 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 in pink that I have on the right. That's going to be what we use to help us determine the error bound, where we take that and add it and subtract it to the .69 blah 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 number. And that's exactly what we're going to do here, where it says find the interval such that from A to B, A is going to be less than the cosine of 0.8. Again, that's the approximate value inside in between where it says cosine of 0.8. That's the approximate value that we just got, and it's going to be less than B. So here, and I'm sorry, I'm just not gonna write these numbers down. Let's call this, because we're gonna save these numbers in our calculator. Let's call this A. Let's call this B. I don't know where you saved them in your calculator. I'm just call it A and B. So here I'm going to say that the cosine of 0.8, oh, I don't know why I wrote that. 0.8 has to be less than. B in this case is actually going to be the cosine of, well, scratch that. This is A. Okay, so I'm going to say A is going to be less than or equal to the accuracy or the approximation plus the error, and this is going to be less than or equal to the accuracy minus the error. So I guess if you really want to, we can change that back to be cosine of 0.8. Okay, but basically we're going to take the 0.697 number and add the 0.0003 number, and then we're going to subtract it as well. And that is going to give me cosine of 0.8 to be less than or equal to, let's see, 0.697430756, but greater than or equal to 0.696702578. And that is the interval that we could say, we're accurate to. So that is going to conclude what we're talking about for the Lagrange error bound and how we determine its accuracy. Or remember, the Lagrange error bound is essentially, once you know the error, we simply just add or subtract that to our value that we're approximating with to get our upper and lower bounds. And that, if you're not given an interval, you can kind of, create your own interval depending on where you know the center is and what you know your value of x is going to be. You can determine what your error is going to be by using Taylor's inequality, and I think that's about it. I feel like I'm forgetting something at the moment, and I'm going to kick myself because as soon as I hit stop, I'm going to remember it. But anyway, ladies and gentlemen, thank you for watching. I hope this has been useful and informative, and thank you for watching again. Hope everybody is well, and take care.